So good afternoon, everybody. Welcome to our today's lecture. It's an invited lecture named Evolutionary Optimization of Neural Network Hardware Accelerators. It is delivered to you by the LUMI AI Factory, but our tutor today is, as I said, invited speaker, Dr. Vojtěch Mrázek. He's a researcher with the Evolvable Hardware Group at the Faculty of Information Technology at the Brno University of Technology. He also held a postdoctoral position at the Technical University of Vienna, and his research focuses on approximate computing, genetic programming, and machine learning. Dr. Mrázek has authored more than 60 scientific publications and received several prestigious awards, including the Joseph Fourier and Czech Mind Doctorandus distinctions. And today he will be presenting methods based on evolutionary algorithms for optimizing accelerators for specific neural networks, as well as for tailoring neural networks to particular accelerators. It will demonstrate how the deliberate introduction of computational errors and the refinement of the organization of computational units and memory can significantly enhance the overall efficiency of the inference. Now I'd like to mention a few practical things. We have already talked about the recording, so this recording will be available after post-processing at the IT4I's YouTube channel. So we would like to ask you for maybe 14 days to post-process the recording, and then it will be released. When it comes to questions, then Dr. Mrázek will definitely make breaks, but at the end of the session, which is not that long, there will be time for discussion. So we would like to ask you to stay muted also for the benefits of the recording, and use chat for questions if you do not want to remember them for a longer period of times, or speak up during the dedicated time, then you can unmute yourself. With that, I would like to thank you for coming, and also Dr. Mrázek for preparing this lecture, and I will hand over the floor to you. Thank you.
So, thank you for introduction. My name is Vojtěch Mrázek. As it was mentioned, I'm assistant professor at Brno University of Technology. I'm mostly involved in EDA, electronic design automation, and this topic is somewhere between the chip design. It's in the chain of the chip design. So it's between the creating of the system and the fabrication. So we are proposing tools for the creation of the hardware layouts or RTL layouts for given applications. So this talk will be about evolutionary optimization of neural network accelerators, and it is divided into several parts. In the first part, I will briefly introduce the problem of the neural network for embedded systems, so what we have to solve and what are the issues there. Then I will introduce three different ways how to save the energy and how to optimize the energy efficiency. The first topic will be about approximate computing, so we will introduce some error to the computation in order to achieve more energy efficient application. Maybe sometimes we got some small error, but it is still acceptable. Then we will focus on the hardware accelerator optimization on specialized case of capsule neural networks. And in the final part, I will focus on the execution planning for convolutional networks and for the transformer networks. So to begin, I would like to introduce the problem, the topic of deep neural networks. I believe that everyone is familiar with that. Mostly that it is very promising topic, and there are many continuing ways like transformer networks, etc. And I would like to mention that there are, in the processing of the neural network, it encompasses two primary phases. So at the beginning, we are training the neural network, and then we are focusing on the inference. The software scientists are mostly focused on the training of the neural network. So we are trying to achieve the best accuracy that we are able to get. But mostly in the applications, we are focusing on the efficiency of the inference part, so the application. And this application we can find everywhere. We can find in embedded systems. We can find it even in some small devices. And the idea is that we have some input data set, the deep neural network is trained. The training is typically done on some GPU cluster that you are very familiar with. And then the trained weights are passed to the inference part. The inference part is somehow optimized for the training data. And it can be done on the GPU, CPU, but also it can be done on FPGA chips or ASIC. So the chips, one ASIC chip is the chip that is fabricated directly in the silicon. FPGA is some kind of the chip where we can modify the function. So it is somehow variable, this variable chip that we are able to control. If you look on the parameters of the commonly used neural network, we can see that the computational intensity of modern neural network represents significant challenges for practical development. The majority of the network inference operations can be transformed into matrix multiplication, making multiply and accumulate operations the most computational intensive components. As we can see in this figure, processing of single image from ImageNet data set, I think it's more than 200 by 200 pixels, requires a billion of floating point operation. And moreover, the modern architecture such as transformer and large language models like GPT impose hundreds of billions of parameters further strengthen the computational equipment. The platforms that we are using for the application or the solving the and training of the deep neural networks varies in the power consumption and as well as the performance, because we are familiar with the superclusters like in Ostrava, like IT4I, but there are some specialized cluster directly from from GPU vendors. But we are also having some small devices with very small power consumption. We can see that the power consumption is from 10 watts to 2 watts only, that are able to provide the inference of the neural network very, very efficiently. The problem is that these platforms are not typically usable for the training of the neural network. We are typically using it just for the inference part, but in the small embedded devices like the some vision on smartphones or some thermostats, there is a need to have good performance for the processing of the neural network. If we compare the neural networks, the most modern neural networks, and the architectures, the accelerators, we can see that we have some trade-off between the power consumption and the speed. We can see that one of the most powerful products are the GPUs, but also if we are limited by the power, the ASIC chips, the purple one, are offering us very good speed, giga operations per second, with very low power budget. So we can see that if we are involved or if we are focused on the low power systems, we need to select some good ASIC solution and some good implementation of the neural network accelerators. There are several accelerators, as we can see here, published in the literature. If we look on these accelerators more in detail, we can see the power performance of different accelerators, like based on ASIC or FPGAs or GPUs, and we can see that, for example, the tensor processing unit, which is one of the embedded system based on ASIC chips, offer us, in this case, this number 128 by 128 matrix multipliers. And the idea or what we are trying to solve is to map the neural network efficiently on the processing of these components and vice versa. We are trying to optimize the organization of the neural network accelerator to achieve the best trade-off between the accuracy and the power consumption. In the literature, the neural network can be categorized into two primary architectures paradigm. the temporal and the spatial architectures. These paradigms represents a different approaches to exploit parallelism and organizing computational resources. The temporal architecture, which we know from CPU or GPUs, exploit the parallelism by reusing of the same computational hardware, so the small uh, arithmetical logic unit, uh, to across multiple operations sequentially. And these allows execute different operations at different time steps, efficiently sharing computational resources across the temporal dimension. The LU receives the data from the local memories and return the results to the same memory. So there are a lot of memory communications. So we are using the lot of caches, and uh, the memory accesses becomes to be main performance and energy bottleneck. Traditional CPUs and GPUs exemplify the typical temporal architectures. The spatial architectures exploit the parallelism by distributing the operations across the same multiple processing elements, PE, that are executing simultaneously in the space rather than the time. Each of them implements a MAC unit, multiply and accumulate small local memory and the controller. And the PEs, the processing element, are organized typically as a pipeline systolic arrays optimized for fast execution. Let's move on some visualization. So basic CPU without any parallelism, when we are performing the inference part, so it is matrix multiplication basically, we are loading weights and features and weights to the memory, and we are getting sequentially the results, and at the end we are able to do the final decision, the final classifications. One can say that we have more modern implementations, like we are using the SIMT approaches that can be implemented on CPU or GPU. And in the GPU, there are many warps working in parallel. So on the GPU, there are 32 processing elements working in parallel, and all these elements are doing basically the same operations, and we got many results at the end. So what is the difference of this temporal architecture to the spatial architectures? The spatial architectures has different organization of the PE arrays. We can see that there are small PE arrays that are connected together. And at the initial phase, we are distributing the weights into the initial internal memories. So this is the initial phase. And in the second phase, in the second step, the data are loaded in some clever way from the different path, from top or bottom. And we can see how the values are processed around the systolic array. And the advantage of this is that we have significantly reduced the number of memory accesses. So in this case, we are using the data locality and the internal connection between each processing element. And since we are saving a lot of memory accesses, we are saving a lot of power consumption. So this is ideal for low power systems. But there are several issues. The main issue is that this architecture is not flexible. For example, we are using in the many architectures fixed architecture of 8-bit integers and 16-bit floats. Another issue is that these chips are typically done in the ASIC processor, so there is a significant cost of the design. And another issue is that the planning of these operations, you can see at the figure that it is very advanced, becomes to be very comprehensive. So it is not trivial to map arbitrary operations to these processing arrays. So let's move on the initial example of ASIC accelerator. The initial architecture becomes to be introduced in 2016, but the current architecture still follows this architecture proposed by MIT team of Professor Vivian Se. And the idea is that we have some DNA accelerators. The DNA accelerators consist of the processing element array, which is here, there are a lot of interconnections, and at the end we are collecting the data. We are able to load the data and save the data to the global buffer. This global buffer is very fast, and but we are, is very limited by the size. And this processing system is communicating with the off-chip memory on DRAM over the bus. And to control this chip, we need to propose some compiler. So we need to propose how to load the data, how to compile the neural network, so how to transfer it to the general matrix multiplication. Then we need to tile the data or tile the processing to the size of the processing arrays, because we are not able to perform here the arbitrary size matrix multiplication, but we are limited by the size of the processing element array. And then if the size of the matrices are larger, we need to tile it to the small parts and accumulate it inside the system. And with this tiling, there becomes another issue. The issue is the organization of the data flow, because we are loading the data, and in the convolutional neural network, there is a good opportunity to share data, because for example, we load the data and we can process it with another features. And there are several approaches. So we can have the data that are the loading that are weight stationary. So we are loading the data to the processing elements, and then we are loading the activations to the processing element, or it can be auto-stationary. So we are loading the activations to the processing system, and the weights are loaded in another step. Or we are not limited, we can use no local reuse, or there are several approaches like row stationary and etc. So this is the organization of the neural network accelerator. But if we look on the embedded neural networks in general, we will see that there are several limitations. One of the limitations, the idea is that we are able to optimize the neural networks for the processing of the embedded at the level of the embedded systems. The first limitation that we have, that in the embedded systems we have a reduced set of the functions. If we have some embedded system that is mostly focused on the inference part only, we are not supporting any backpropagation task, and mostly the set of the operations is limited, for example, to this data set. This set of the functions is taken from TensorFlow Lite. So from the modification of TensorFlow framework that allows to be trained on the embedded systems. Another approach is to prefer depth-wise convolutions. What the depth-wise convolution is? In the standard convolution, we have some data, for example, 12 by 12 matrix with the depth of 3. And it is multiplied on convol by the filter 5 by 5 by 3. And at the end, we got the final set of output. However, we are also, or it was shown that if we are using depth-wise convolution, so we divide the convolutions to 3 independent steps, as it is illustrated here on this figure, the memory reusing can be significantly higher. And with this advanced organization of the memories, we can achieve significantly better energy consumption and significantly lower number of memory accesses, especially in the embedded systems. And the crucial question is, do we really need to run inference at the edge? And the answer is that yes, we need. Because if we know that there are very good clusters, and the energy efficiency, for example, on high-end GPUs is very good for the processing. There are several limits that we need to consider. First one is the cost of the communications. If we imagine that we have, for example, some sensors in which is battery powered and it is somewhere in the mountains, there are several applications, for example, for determining or snows issues in the mountains. We need to have the sensor, which is typically installed by a helicopter, to be battery powered and running for several years. And in that case, we are not able to send all the data over the network, some communication network, because it is the energy consuming. In our case, it is performed the classification at the edge and just to send the final data, the final information, yes or no, or the classification of the data, instead of using of the raw data for the processing. Another issue or another motivation is privacy. Because in the embedded systems, everything is executed at the edge. For example, if we have intelligent thermostat for regulating of heating, we don't need, which is voice controlled, we don't want to capture all the sounds from our room and sending it to the cloud because it is not needed to capture everything. So in that case, all the speech recognition is done at the edge and everything is working independently. Moreover, this inference or these neural networks are very simple because we don't need to process everything like in large language models. We need to process 32 of voice commands that we need to recognize. So it is much simpler and we need to done it just efficiently. And another issue is latency. Because for the latency, for example, in the automotive industry, we have many different sensors, and we need to make some, for example, in the autonomous driving, we need to make the control operations, the final operations, very fastly with slow latency. And we are not able to go over the inputs sequentially to process everything. So, in that case, we are transforming this data or this processing to the, for example, FPGAs or ASIC chips that are able to capture more sensors in parallel and do more tasks in parallel with low latency. So, what are the challenges of the embedded neural networks? So, as I mentioned, we have reduced set of the layers. Another issue is that we are mostly not working at the integer representation. So, if we look to the conference presentations about the EDA, electronic design automation, we can see a lot of paper that focus on the problem of the quantization. So, we are trying to propose the best quantization schemes to have good accuracy and to achieve a good performance. However, there is an issue that if we are using fixed point representations or fixed point quantizations, there is low dynamic range of the integer of these operations, and it can cause many problems in the training. So the quantization is typically done post-training, or there is some just adaptation for the data, but the training is done with the floating point accuracy, and the quantization is done after that. Another issue is that the resources are very limited because the memories that we are using are very small or are using limited memory bandwidth. But as I mentioned, we are not only needed just to perform very large language models or the best neural networks that exist in at this state of the art. In the embedded systems, we can also use the small neural networks and small systems. And the most crucial issue that we have is the energy budget. Because these devices are typically battery powered, and we need to introduce we don't need to spend the battery and replace the battery or charge the battery every day. So we need to achieve a good energy consumption. And we can move to the next topic, which is called approximate computing. Approximate computing is one of the paradigm for the design of the energy efficient systems. And it is common in every operations, because with the increasing complexity of the computational system, we can the performance is growing up. However, the power consumption is growing up too. The researcher tries to address these problems by introducing modern technologies and design techniques. So these design techniques and modern technologies help us to reduce the power consumption while achieving the same performance or better performance, but there is still some limitations. However, many computationally intensive application features an intrinsic property which we call error resilience, because the data that we are capturing are errors, and all the data, all the representation of real-world systems are only approximation, because the floating point is not the real floating point. It is some approximation, and we are not able to have everything inside it. So the idea of our approach is to uh, exploit the fact that users are willing to accept certain errors in some cases. And especially in the signal processing or image processing, we can accept this. So we are introducing some small error into the computation while achieving some power consumption reduction. So if we move to the topic of the neural network accelerator, we can ask where the approximation of the neural network can be introduced. So if we have some neural network, we can modify uh, this representation of the data or the weights, so we can reduce the bit width of the operations. This approach results in many different ways. So we have more optimized computation and calculation of the weights. So the Mach units that are in the systolic arrays are more efficient. And moreover, the weights that we are storing to the memories are, in this case, occupies smaller space. So, for example, if we have 40-bit, 64-bit bus, and we have 8-bit representation, we are able to get 8 elements per tact, per cycle. But if we reduce the size of the weights to 4 bits, we can, instead of 8, we are able to get 16 elements in one cycle. So in that case, we can achieve the two times better latency. Another approach is to modify the architecture of the neural network. So we can scale the architecture, so we can remove some layers or some neurons. We can do it for the training neural networks. It has been done in small neural networks, like based on MLPs. But if we look on the standard neural network, for example, for a ResNet neural network, it can be scaled. We have ResNet 18, we have ResNet 51, and we can somehow scale the architecture by introducing several type of the layers. And another approach is to introduce approximate component. If we look on this example, this is example of the hardware implementation of 2-bit adder. We can see that there are 2-bit A and 2-bit B, and this is the small implementation. This is basic implementation of this adder. But if we are accepting that 3 by 3 is not 7, is not 9, but 7, the implementation is significantly smaller. We can see that there are only 5 gates for this implementation. And this is the general idea of approximate components. I will focus on that in the next part of the presentation. And which level of the energy savings is the best? So the best way is to perform the cross-layer approximation. So to combine all these approaches together. If we are talking about approximation and the approximate computing, now we will mostly focus on this part. So the using of the some errors elements inside the computation. If we look on the approaches for the introducing the error, there are several ways. One of the approaches is physical approximation. This physical approximation somehow plays with the technology, And we are scale the voltage, and we can, this approach is called near threshold computing, because all the transistors at the silicon has limited, so has some limits where can they operate. And if we are trying to achieve this limit, is called threshold voltage. And if we are trying to achieve the voltage which is near the threshold voltage, sometimes the computation is not correct, but it is power efficient. Another approach is to use inexact memories. For example, the standard SRAM chip consists of 8 transistors, but if we are using 6 transistors, sometimes the output then can be some bit flip at the end, and we need to somehow, it can be errors. But if we use these smaller cells with 6 transistors just for savings of the LSBs, it becomes to be more efficient. Another approach is architecture approximation. This is the highest level of the abstraction. So it is function skipping or data precision reduction or some inexact models. So instead of calculation of everything, we are proposing to make some regression with something more efficient. And we will focus mostly on the topic of the functional approximation. The functional approximation is simple modification of the Boolean functions of the circuits, while the rest of the tool flow, the synthesis and implementation tools, so the translation of the VHDL code or Verilog code and RTL code to the chip design, so the organization of the chip layout, keeps same. The advantage is that the commercial synthesis and implementation tools are well tuned, and it is not easy to achieve same results, and sometimes it is not possible. And it can be denoted to 2 major tasks. One of the tasks is design of approximate components, in particular address and multipliers, because as I mentioned, the PE processing arrays mostly consists of the multiplications. So in this case, if we are proposing some more efficient, if we are saving, for example, 50% of the energy of the multiplication, we are saving 40% of the energy consumption of the systolic array. Another approach is the higher level approach is to high level approximate synthesis of complex hardware accelerators. So if we have the library of approximate components, the task is assigning of the components to the computation. Let's move on the first part. So it is the design of the approximate component that can be used in the neural networks and in the efficient for the efficient neural networks. So let's move. So we will look on the approximate components. And I briefly mentioned that, but just to recap that, the elementary units can be replaced by approximate implementation. This is the very pioneering work of the inventor of this idea. And if the users are willing to accept this error, the power savings becomes to be 37% just by this small error. However, this approach is not very scalable for the application for larger 8-bit or 16-bit multipliers. Another approach is some regular modification of the structure. For example, the classical multiplier that we have consists of the processing element. There is one multiplicand, there is second multiplicand. We can see that it is done by, this is some full adder or adder, 1-bit adder, and it is processed in the regular way. And if we are removing or omitting these cells, we achieve very good performance between the error and the power consumption. Another approach is to cut the longest path of the circuit. So this is the way that is limiting us, that we have chain of the processing. For example, for addition, we need to have a carry bit that is propagated through the computation. So if you have large address, it becomes to be very difficult to have a good timing, and the timing is very limiting us. And if we are not able to achieve the good timing, we need to use the more efficient or more effective cells, but these effective cells has a larger power consumption. Or to exploit some mathematical properties of some circuits. So, for example, we are able to transfer the calculation to the usage of the logarithmic adding. So we are transforming the representation to the logarithmic logarithmic base. So what, however, this is the manual approximation, which is not scalable. However, for the design of the approximate components, we need to have some design methodology. And the design methodology is some process that takes some original circuit and some quality metric. In the area of the arithmetic circuit, it can be arithmetic error, mean arithmetic error. So for the all input combinations, so for 8-bit adder, there are 65,000 of input combinations. And for all these combinations, we are calculating the error and what is error with respect to the original circuit. And we can have a mean error or the worst case error. And there are several automatic approaches for the design of the approximate circuits proposed in the literature. So if we have this automated design methodology, we will focus on the search-based evolutionary synthesis, which is guided by some evolutionary algorithm. We will use the evolutionary algorithm in the rest of this talk. So the evolutionary algorithm is some approach where we are optimizing its design space exploration algorithm, typically single objective, but we can transfer it to the multi-objective uh, domain. And the evolutionary algorithm and the evolutionary design works in general as follows. We have some engine which produce some encoded solutions, typically set of integers. Then we decode this integer netlist into the circuit, and we put it into the simulator. In this simulator, we calculate the so-called fitness function, which tell us how good the circuit is. So it can be the area optimization or the functional approximation, and it return us the fitness value, which is one value that represents that is comparable. And based on this loop-like, we generate a new solution. So it works in a loop, and we need to perform several steps and several iterations, thousands or millions of the iterations to get a better solution. The evolutionary algorithms has several questions. First is the representation of the circuit, then the fitness calculation, how to do it effectively, and then how to generate new solutions. The representation and generating of the new solutions is already solved by using so-called Cartesian genetic programming. Cartesian genetic programming is an approach where we have a grid of the nodes, regular grid, that is fixed. It doesn't change during the search. Each node is represented, or the grid is represented by the integer netlist, where each triplet, in our case, represents the connection. First integer value gives us the connection of the first input. The second integer value gives us the collection of the second input, and the third integer represents the function of the node. And at the end, we have a connection of the outputs. And by the modification of these integers, we call it mutations, we are completely generating a new circuit. For example, by reconnecting of this output to this one, this part becomes to be unuseful, so it won't be active. But this node becomes to be active, and the function will be different. So this is the mutation, and the search algorithm is based on 1 plus lambda approach, 1 plus lambda searching algorithm. So we have some original circuit, and we propose some small change. However, we can see that it doesn't improve the fitness function. So we try to generate a new one, another one, with, which has same accuracy and the same quality or the same area. And we are iteratively trying to propose some small changes, and we are accepting the changes that led us at least to the same solution. So to the solution with the same quality or better. And there becomes to some one very crucial question, how to calculate the quality. The quality is a fitness calculated by fitness function, and it is the key operations in the genetic programming. It's a scoring of the candidate circuit where a better solution obtains a lower score. In our case, we need to correct multi-objective optimization, the error optimization, with the approximation parameters, so the error. And the fitness function works as follows. The fitness of the candidate circuit is the size if the error is below some given threshold. Otherwise, it is infinity. So the solution because the initial solution satisfied this constraint, we wouldn't ever accept some solution that doesn't satisfy this constraint. So we will see that during the chain of the approximation, we will improve or having the same size. And the size is estimated by the weighted size of the all active gates, and it is multiplied by the quality of the size of in the fabrication technology. There is some good advantage because if we, for example, we don't need to focus only on CMOS technology. We have some applications, for example, in the printed electronic, where you can print your own circuit on some flexible or on some pad, and it can be printed by some specialized printer. The problem here is that the behavior of the gates is not same. The area is not in the micrometers, square micrometers, but in square centimeters. And in general, the behavior is different, and we are not able to use standard logic synthesis tools. However, if we are using the evolutionary algorithms, it can propagate that, for example, NAND gates are more complicated than AND gates in the flexible in this printed technology, and the evolutionary algorithm can handle these approaches. If we look on the results, we can see that we can see a comparison between the worst case error and the power delay product, the energy of these multipliers. And we can see that our approaches to design of the approximate components were significantly better. You can see the Pareto front, we are trying to move towards this point. So these components becomes to be significantly better than the components that we were using or that can be found in the literature. And this approach has been found as human competitive. There is a big competition in the evolutionary computation community to propose some algorithm that is better than human designed circuits. And our research has been devoted that it is human comparative and the evolution was better than the design of some engineers. So using these approaches, we create a library of approximate components. So for each bit width, we proposed thousands of different multipliers. Each point here is one multiplier. So we can see that there is a good trade-off between the error and the power consumption. And this library is a basic building block for high-level approximation, which I will move towards now. However, there are several questions of this approaches I have already introduced, and there are issue of the scalability of the evolution because the calculation of the error becomes to be very problematic, and we need to use advanced dataset or some formal verification approach. And there is also issue of scalability of representation. For the design of large circuits, we have problem that it becomes to be very large and to propose some errors. So we are using some cutting algorithms to have a better trade-off and to improve the quality of the circuits. So let's move to the application to the neural networks. So if we are using approximate components in the neural networks, we can use several approaches, and we are using our approximate multipliers for the approximation. And moreover, we are trying to achieve this approach, to target this approach without any retraining. So we are trying to introduce the approximate components directly to the computation without any retraining. So there are several challenges. If we are trying to employ some approximate component for example, for all layers, it becomes to be problematic because each layer has different sensitivity for the errors. For example, the middle layers are less error sensitive like the initial or the output layers of the neural network. So we propose some algorithm to assign the approximate components to the layers. Another issue is, or challenge is, how to obtain a good trade-off between the accuracy and the power consumption. And there, in this case, we are trying to propose some design space optimization, which is guided by the evolutionary algorithm. It is multi-objective approach for the optimization. And another challenge, which is also crucial for the design of the approximate accelerator, is that we need to handle the behavior of the approximate of the accelerators, and we need to be accelerator centric. So there are several types of the architectures of the accelerator, and we need to propose some encoding that will handle the organization of the accelerator. So let's move on the results that we have. And we were using an NSGA2 optimization algorithm. This algorithm, it's 20 years old optimization algorithm. There are some better already proposed in the optimization in the era of the people doing some multi-objective optimization. But interestingly, in the area, in the community of the hardware designers, it is well used algorithm because it is one of few algorithms that is proposed to give that is giving us some trade-off between some parameters, which is typically done in every design that we are trying to propose, because every time it's some trade-off between area, latency, and power consumption. Uh, and the more advantage, algorithms are typically focusing on some benchmarks with several different objectives. But since we are limited just to two or three objectives, there is no need to use more advanced algorithms. So in our case, we are trying to assign one of 20 approximate multipliers that we have in our library to one of the 50 layers. It looks like very simple task, but in general, there are 10 to the power of 65 combinations that we need to handle. So it is not feasible to try to search everywhere. So we are using the heuristic design space exploration based on NSGA2 algorithm, where we start with some initial population, so initial assignment of the approximate to one of the layers. Then we generate a new candidates, and these candidates are evaluated. And this is the crucial aspect of the searching algorithm, because for the evaluation, we need to calculate the energy consumption. We can somehow estimate it by we can weight it by number of multiplications and the power consumption of each multiplier. But for the evaluation of the accuracy, we need to run the optimization algorithm, or for example, some TensorFlow, which implements approximate components, so the emulation of the approximate component, in order to achieve the accuracy. And if we have these values, we simply select the best elements from the set of the parent and the offsprings and run this algorithm iteratively. What is the key idea of the NSGA2 algorithm? The key idea is the sorting to Pareto fronts, because we know what is Pareto front, and if we have some population which is evaluated, we perform the non-dominated sorting. So we got the first Pareto front, then we get a second Pareto front, which is below that. Then we get a third, fourth, fifth, sixth. And if we have some if we have to cut one of the Pareto front, there is some specialized algorithm called distance crowding to get a new parent population. So this is the idea of the searching algorithm. And another issue is the representation of the system. If we imagine how the algorithm, how the how the accelerators looks like, it is somehow organized to the ties of the processing elements. Please know that this is mostly hypothetical architecture because this architecture has not been fabricated, but it is based on the existing architecture. And if we imagine that, if we propose that we can divide the chip to several areas, and each area has several type of the approximation, we can see that the number of the approximation is limited. We cannot use 50 different multipliers for 50 different layers because we are not able. We need to create the approximate multipliers, especially for one chip. And this is the case that we are able to inherently handle by the evolutionary algorithm because the evolutionary algorithm, uh, we can limit it to have only valid solution. And the best way is not to limit it during the evaluation, but during the creation and at the level of the representation. So we propose one architecture which is called pipeline. So the representation is divided to two parts. First part says that, for example, if we have three tiles, so up to three approximate multipliers, the first tile is limited to first tile has one multiplier, second tile has different multiplier, third tile has another multiplier. And this is the representation, this is the permutation of the inputs that we have. And at the end, we can see that initially we are performing the layer 1 at tile 3, then the data are transferred to layer 2, then the data are transferred to layer 3. And this is the second representation that doesn't need the permutation of the input. So this is different representation, but the general idea is that we are able to handle arbitrary uh, constraint to the representation and have it more effective. So then we are proposing the methodology that is working in the level of the approximate on the level of the evolutionary algorithm. So we are assigning the approximate to the tiles and layers to the tiles. We are somehow updating weights. I want more focus on this topic, but then we analyze the accuracy and the energy efficiency, select the best assignment using NSGA2 algorithm, generate a new candidate solutions, and at the end, we are doing this algorithm in the loop. And at the end, we are proposing the comprehensive analysis to achieve a set of the Pareto, set of the approximate accelerator. Let's move to the results. If we compare our approach with the uniform structures and several structures, we can see that we achieve significantly better right Pareto fronts. So we are needed to get to this point. This is the optimal point. So we have significantly better Pareto fronts in the area of the energy multiplication and the classification accuracy. And for the results, we can see how the algorithm works. So this is the run of the one algorithm. So it's iteratively improving the accuracy from the starting points, the blue one. And if we compare these results with the state of the art, we can see that we were able to achieve uh, the solution for most comprehensive set in 1 hour instead of using comprehensive retraining and so on. And if we compare the data with the state of the art, we can see that we were able to achieve 30% power reduction with only 0.6 classification accuracy decrease. And similarly, compared to different approach, with the same power or energy savings, we have 3 times smaller accuracy drop. And this approach can be useful, for example, in the case where we have no training data available, or the architecture cannot be scaled, or the training time is larger than the time of our algorithm. So, for example, if we have this algorithm, this neural network, from this point, we are able to achieve this Pareto front, and we can combine it with the scaling of the architecture. This approach can be combined with another approach, and the approach is called neural architecture search. It is common work and common approach how to get the optimal neural network architecture, and the researcher mostly focus on the optimization of finding most suitable neural network architecture for a given data set. So the researcher were trying to search for the best architecture. The neural evolution has been done in the evolutionary algorithm community since the mid of 80s of the 80s, but it was done at the level of multi-layer perceptron neural network. So the researchers were trying to get a bet to find the best combinations of the neurons, and it was very small neural networks with 5 or 10 neurons. However, after the heap of the convolutional neural networks, after Jan Lečun research of the LeNet and AlexNet on all these cases, the neural architecture search has been connected with the DNNs and combined with the high performance computing, and the big tech companies try to search for the best architecture and with the best accuracy. But this is a problem that they focused only on the single objective approach. So they were trying to achieve a best accuracy without any uh, consideration of the hardware parameters. So what are the approaches for the search? One of the approaches is that we are trying to propose all uh, the connections of the networks of the layers in the neural network. We can have some string representation, and we can propose the connection like the CGP that I've shown before. This search can be divided to the several types of the search space. One of the search space is the macro search space, where the entire CNN is encoded, and we are trying to propose all the CNN. Another approach is to have a regular structure of the cells, and we are trying to search of the small cells, and we can combine it together. So we can have some in the hierarchical space search or indirect encoding. And another approach is to use supernets. The supernet is a large neural network that is pre-trained at the beginning, and then we are trying to prune it. So this is another approach. So we have some starting here. We are typically starting from scratch, and we are trying to improve the solution. And for the supernet solution, we are trying to remove some parts in order to achieve better efficiency. However, as I mentioned, the researcher and big tech companies focus mostly on the single objective NAS, but for the hardware designers, there are the crucial aspect of the energy consumption. So we are able to transfer the searching algorithm with some additional objectives like latency of the processing, area, energy, size of the memories, reliability, and so on. And what is important, the hardware is not optimized in this case. We are trying to optimize the architecture of the neural network that is executed on the hardware. And if we check the target neural network in the research, we can see that most of the architectures focus on the GPU and CPU processing. And this approach can be extended by application of the approximate layers and approximate operators. So instead of uh, using of the standard convolutional layers in the neural architecture search, we are also proposing to use the approximate neural network, approximate convolutional layer with some level of the approximation. So if you look on the results, from the results of the Michal Piño's works, of my colleague, we can see that this is our former approach, L1, that we have. And this researcher was able to achieve significantly better accuracy and significantly better trade-off between the energy of the multiplication and the energy consumption. Moreover, there are several, or the issue of this search, or all the NAS neural architecture search, is the calculation of the accuracy. Because if we are performing the standard search, we have some representation of the neural network that have to be trained and then test. And using this approach, we got the final accuracy that is input for the search algorithm. And if the training of the neural networks takes 10 minutes or 1 hour, and we want to, if it takes, for example, 1 hour, and we need to perform the neural architecture search for 200 solutions, it would take 200 hours for the search. And it becomes to be very computational intensive. And all the experiments that are here has been executed at a computer cluster in Ostrava. And it is time and energy and money consuming approach. So we are trying to shorten the evolution time. And one of the approaches is to employ some proxy data set or reduce the number of the training epochs. So we are training the data neural network just for few epochs. Or extrapolate the learning curve, so we know the learning curve, how it looks like, and we are trying to estimate the behavior from this curve. Another approach is to build a surrogate model, some accuracy predictor, which can be based on the neural network. So we are trying to build a neural network that is predicting what will be the training accuracy for some case. And interestingly, this approach is also somehow working. Another issue is the calculation of the hardware metrics. So we can run the neural network directly in the hardware, or we can use some surrogate model that will try to estimate the energy consumption based on the number of the multiplication and number of memory accesses and etc. So this is the optimization of the neural architectures, and introducing of the errors. Let's move on the optimization of the hardware accelerator from the different side, from the optimization of hardware accelerators. So we will try to optimize some accelerator for the capsule neural networks. What is the idea? The idea is of the capsule neural networks. It's specialized case of the neural networks uh, investigated by Saber and Hinton from Google that they proposed some enhanced type of the deep neural networks that has a multidimensional capsules instead of unidimensional neurons. So the ability of they have ability to encapsulate hierarchical informations or different features like position, orientation, scaling in a single capture. And this approach allows us to achieve higher accuracy in computer vision and application. Unfortunately, this approach it is based on our research, and it was very promising. But at the end, the transformer neural networks outperformed the capsule neural networks. So now the capsule neural networks are not very famous. But what I want to illustrate on this case is not the idea of the capsule neural networks, but we have a nice accelerator for these neural networks. And I will show you how can we optimize the neural network accelerator for this use case to achieve better accuracy. But at the beginning, I would like to mention the basic difference. So in the traditional deep neural networks, we have neurons with scalar values. In capsule neural networks, there are vectors. Instead of weighted sum and nonlinear function, there is a complex vectorial function called squash function. And instead of using pooling layers, there is so-called dynamic routing, which results in very comprehensive behavior from the memories. And the idea is that instead of detecting of features, we are trying to detect entities. If we look on the architecture of the deep caps CapsNet architecture, we can see the architecture where we have some input and where we have the arrows. The data are not single scalar values, but they are vectors that are performed using. We have the input convolution layers, primary capsule neural networks, and then is the dynamic routing algorithm. This is denoted by the red line, and you can see a back loop that is here that becomes to be very ineffective in the hardware and must be solved directly at the hardware level, this by some bypasses in the memories. Another architecture is deep caps architecture that also consists of three-dimensional capsule neural convolutions. And here's are the capsule convolutions. And at the end, or here, we have the dynamic routing algorithms. And all the neural layers are followed by the squash algorithm. So it was brief introduction of the capsule neural network, but my approach is to optimize the accelerator for that. So firstly, I would like to introduce the architecture of the accelerator of such neural network. So the initial part of the neural network accelerator is the systolic array. We have the systolic array where the weights are coming from the upper part, the inputs are coming from the left part, and at the right part, we have some outputs, and here we have the partial sums. And these inputs, or the systolic array, consist of processing elements that has the multiplier, some register for the weights, data register, and some summary register. The data are processed and are stored in the accumulator, which is some buffer for the accumulation. Then the activation unit is done. So we have the calculation, and it is approximate the function of the ReLU normalization squash function and softmax function. And there is some loop of the data memory and the routing buffer, and it is running in the scheme that I introduced before. So this is the architecture of the capsule neural network that was proposed by Alberto Marchisio, that I collaborate strongly with. And the idea that we are trying to propose is to how to optimize this accelerator. So we have this accelerator, we have the neural network, and we are trying to optimize the parameters of the accelerator. And for this approach, we proposed FECA methodology. And this methodology tries to optimize the parameters, the hyperparameters of the accelerator. So what are the parameters? The parameters can be the number of input pairs that are done, that can be processed in one processing element. We can optimize the output precision and input precision, but we don't care about that because this affects the accuracy, but we don't want to affect the accuracy. We can divide the pipeline to several stages. So we can add some registers here during the calculation to achieve a better frequency, but because of the pipelining, there are another issues. And also we can play somehow with the dimension of the array. So we can define the number of rows and columns. So with this definition, we need to put it to the overall methodology. So we have configuration of the memory, also the memory parameters, and so on. And we have the input architecture of the capsule neural network and the design objectives, what we want to optimize. We have the searching algorithm, which is guided by the evaluation. The evolutionary algorithms is standard NSG2 algorithm, or for small cases, we can use some brute force search if there is a limited number of the configurations. But what we need to have is some model that give us information how many cycles and what will be the power consumption of such configuration. But as I mentioned here, we can translate the configuration for the hardware representation. So the PEs can be compiled and can be cached or precompiled using the commercial tools, synthesis tools, so we can get the power consumption of each processing element. The Capsule model, Capsule access ACC model, gives us information how many cycles it would take to calculate and to get the power to process the neural network. And cacti model gives us the parameters of the memories. So we know how many joules it would take to read one byte from the memory with some configurations. And this is the input for our search. And we can see that we were able to achieve nice Pareto fronts. This figure illustrates the difference of the brute force and NSG to algorithm search. Because for smaller neural network, we were able to use brute force algorithm to evaluate all the design objectives, all the design combinations, and we compare it with the heuristic search, and we have found that the design space algorithms was able to achieve almost same solutions, the orange one, like the brute force algorithm. So we were able to reduce the exploration time from 2.5 hours to only 30 seconds while identifying more than 150 Pareto optimal solutions. And it was for the smaller type of the neural network, and for the larger type of the neural network, we were able just to run the NSGA, the heuristic search. What is interesting is that we have several types of the layers. The red points show us what are the Pareto optimal configurations for each individual layers that we are using. And the blue parts are showing us what are the Pareto optimal solutions for the whole neural network. What is output of this information, of this figure? The conclusion is that the primary capsule layer is the most power-consuming part, as can be seen on the x-axis, and everything is guided by this layer, and the rest of the layers are just negligible in contrast to the primary capsule layer, and therefore the evolutionary algorithm is also able to handle these properties. So some layers are more significant and some layers are less significant. So it was the organization uh, of the architecture of the accelerator, but we can also focus on the organization of the memories, because on the same accelerator we have the processing array, and we have some on-chip memories for the weight, for the data, and the accumulator. And we have also the off-chip memory. The off-chip memory is typically DRAM, and this is the cost but fast on-chip memory. And the idea of this work is to organize the memory of this accelerator. So we need to store the weights, the data, the features, or the data coming as the features, and the results in the accumulator that then inputs to the activation part. And we proposed to have several modifications of the architecture. So we can have three different separated memories, one for the weight, one for the data, one for the accumulator, or we can have one three-port memory. So we have several ports here which is shared for all the data. And another configuration is to have some small part of for the dedicated memories, and some part of the data are in the shared memory. And the idea is how to organize the configuration of this memory. So number of ports, number of bit width of the ports, and the organization, or dividing to the banks, because the memory is divided to the banks. Then we can also use the power gating, so some banks can be switched off during the computation. So the idea is to optimize the organization of the memory. So what can we optimize? We can use shared buffers. we can use the power gating of the memories. And for the architectures that we have, we can see, for example, that on the x-axis we have the layers that are used, and on the y-axis we have the memory usage. And we can see that, for example, in the hybrid memory, which is this one, this is the hybrid memory. So in this hybrid memory, we propose to store this data in the dedicated memories and the gray data to store in the shared memory. So how to optimize the parameters? We are also using some design space exploration. In this case, the design space don't especially need to be guided by the evolutionary algorithm. It can be guided by the standard algorithm, standard brute force algorithm, because the number of the space is limited, because there is only 1,000 of the 100,000, 1,500 of the designs of configurations, but it works in similar way. So we have some model, some input model that is extracted to the layers. We have some analyzer that give us the number of the sizes and number of the reads. And we have the design space exploration, which is combined with the some synthesis tool and some memory modeling tool. And based on the configuration, we are trying to get the power consumption, to get the memory organization, to get the overall energy and area, to get the overall Pareto optimal memory organization for Pareto optimal energy consumption and the area. So if you look on the results, we propose to have shared memory, which is here. So the shared memory is not effective. And in our case, is to use separated memory, or to use separated memory with the power gating, or the hybrid approach. And the power gating, you can see that the power gating is a very effective approach, because it is the separated memory, shared memory, gives us only one solution, because there are no another combinations. But however, if we are proposing to have power gating, we can divide the number of banks that can be switched off. If we have many banks, there will be some overhead of the switch, larger overhead of the switching on and off. And if we have lower number of the banks, it becomes to be more effective, or the granularity of the switching will be very low. So let's look on this hybrid propagated area solution, and this is the organization. So you can see two rectangles at the blue line. So we have 25, 6 kilobytes in this memory. I don't remember the exact numbers, but you can see that in this case, the blue memory for the data is switched off. So we are using this bank only for the first layer. For the weights, we are different granularity of the switching. So 3 layers, 3 banks can be switched off for first 2 layers. But for the fourth layer, we have to switch it on. So there is some overhead of the switching on. But we are using the whole weighting buffer. Then we are switching off 2 banks, and they are switched off for the rest of the computing. And the shared memory is switched on only for this part. Yes, for this classification, we are switching on the shared memory. So this is one of the results. And this is the distribution of the data. We can see how many power consumption is given from the static energy, and for the dynamic energy and wake up, how the energy is divided to different parts of the computation of the memory banks. So that was the optimization of the accelerator for a given neural network. And the very last part that I want to focus is the planning or the modeling of the neural networks. Because the execution planning, how the calculation will be done, is crucial aspect, because it can affect the overall efficiency. And at the beginning, I will focus on the convolutional networks. So if we are trying to model the AI accelerator, the design space is very huge for the exploration because there are different historic array configurations, different memory hierarchies, number of ports, memory buses, and more and more and more. And analytical modeling offers the most feasible option for the design space exploration. However, if we are running the RTL simulation, we get very good results, but it is time consuming. And in our case, we propose our simulator, which is based on the simulation in a cycle accurate simulation of the processing of the neural network at some given accelerator for the calculation of the memory of the energy parameters. And why we are doing this? Because at the architecture stage, we are able to use some analytical estimation model to achieve the energy. However, the modification at the architecture stage is the simplest one. If we move during the design to the RTL representation and we are using some cycle accurate simulator, the estimation of the parameters becomes very comprehensive, but the most comprehensive is for the physical layout because at this level we are simulating the model by physical equations, so some differential equations, to achieve the overall behavior, and we don't need this level of the certainty uh, uh, of the approaches. However, the existing analytic tools are not designed to handle transformer for irregular memory accesses patterns to transformers. So, what are the existing analytic tools? One of the most famous tools is Accelerators or Maestro. The Accelerators comes from the group of MIT, which I have introduced at the beginning from the Vivienne team, and it is a very good tool that gets the neural network models, has some energy table, so it works in similar way that we were using in our algorithms. So however, it is somehow generalized, and what is advantage is that it is doing the planning. So it is considering the fact that some data are row stationary, wait stationary. We know what is stored directly in the memories, and we know how many loads are needed, how many loads from the wait buffer or data buffer are needed. Another tool is master tool that works in the similar way. So, what this approach can tell us? This approach can tell us for some, it works in a layer-wise scheme. So for each layer, it can optimize the mapping of the operations to the processing element. So to find the best mapping model. So uh, if the data how the matrices will be tiled and what will be stored in the registers during the computation. And you can see that the different tiling can significantly affect mostly the energy of the DRAM, so the off-chip memory. You can see that the Mac memory becomes to be same because we need to perform the same number of the multiplication for one convolution because it is well known. But we can somehow play with the loading, so the consumption of the register file or the consumption of the DRAM. For example, in this case, you can see that the memory of the local buffers is significantly lower than in different cases. However, for the it is uh, it is done by the DRAM energy consumption. However, these mappers, for example, the time loop has an issue that it doesn't model. It is just an analytical model. So they knows for fun configuration how many accesses there will be. And one of the crucial aspects is that they are not calculating with the real hardware and with the real limitation of the hardware. Because we have some architecture, for example, for the transformer neural networks, we can have many more historic arrays to handle the multi-head self-attention array. We have several ports, we have one share, for example, one share RAM, we have of chip memory. So this is one of the input, the hardware specification. Another input is the workload specification. So we have the layers and we have the dependency of the layers. So we cannot calculate the operation tree until we don't have calculated optimal operation one and operation two. And the output of this approach is that we have the schedule that on the systolic array, we firstly want to calculate operation one. On the systolic array, we want to calculate operation two. And on the systolic array, then we want to calculate the operation three. And what is the idea of these simulators? So the idea is that we can perform the something like cycle accurate simulation. So at the beginning, we want to make the operation one and operation two at the systolic array one, but the data are not available. So we want to load the data. We are loading the data from the SRAM, but only this one. But we are not able to load weight one, weights here and weights here because the port is not available. We are using it. So we are loading the weights one, but these features can be loaded to the systolic array one. Then we can run we can load another data. Then we have to stall because we are also loading data and no port is available. And we are doing this in many ways. And in this case and this case, or this time, after 170 cycles, we were able to run the calculation of the operation one. Then we were able to calculate the operation two. Then we are storing the data back to the shared memory. And we are able from this historic array and load it, or we are loading it here, and we are able to calculate the third operation. And then store it right back to the memory. So this is the simulator that we proposed recently, 2 weeks ago. And what are the possible applications? How can we more optimize or how can we more use these approaches to the optimization? So it can be used in several cases. It can be used for advanced planning of the operations. So, for example, if we have this computational graph, it is more comprehensive, and what should be executed on each systolic array. So this is one of the question. And another question is some design space exploration for the organization of the memories, organization of the ports, and so on. So this is another way that can be solved, and we are trying to address in the area of the embedded systems. So now the time is going. So now I would like to conclude with some remarks. So deep neural networks are now important also in the embedded systems, and we don't need to focus only on the most advanced tensor or transformer neural networks. Transformer neural networks or some large LLMs. Another thing is that the neural networks exhibits a error resilience property, so users are willing to accept some error if they have the power savings. And for example, in the error, we are able to achieve significant 30% power savings in the multiplication with only 0.6 accuracy drop. And the proposed method are available as open source software at our GitHub, so it is available here. And finally, I would like to give acknowledgement mostly to my collaborators, to my former supervisors, and my PhD student, Jan Kluhek, which is mostly working on the transformer simulator that I introduced at the very last part. And my large thanks goes to my collaborators from New York University in Abu Dhabi, which I have done my postdoc with, and a lot of research based mostly on the capsule neural network was done with them. So with Professor Muhammad Shafiq, with Muhammad Abdullah Khalif, with Bharat Prabhakaran, and Alberto Marchisio. So that's all from my side. I would like to thank you for your attention. And if you have any question, please don't hesitate to ask me.
Thank you very much for the lecture. I think it was excellent and very informative, and I hope that our attendees or our audience has the questions that we are awaiting. So you can either ask in the chat if you don't want to speak up, or just feel free to unmute yourself and ask. Thank you very much.
Okay, so thank you very much for your attention. I was honored to present our work to you.